Can you all hear me out there? So Carly, just read your chat message. Yeah, if you want to put a list down in the chat, we'll see if we cover those. If not, we'll make time to cover the concepts that you want to go over. So just go ahead and put that in the chat. So yeah, based on the list that you wrote there, we should hit upon each of those topics today in the structure elucidation that we do. So if we don't, just make sure to either unmute your mic and remind me, or put a message in the chat. We'll make sure that we cover it. So we have about a minute before we get started. So I'm looking at the participant list. Most of the names are pretty familiar in terms of showing up to these. Again, the chat, it's not mandatory by any means, but I would encourage you to you know, have your peers in the class, people that you know, show up for these, or watch the recordings on the YouTube channel. Again, you really want to keep close contact with this course so it doesn't sort of get beyond beyond your control, in a sense. So we'll go ahead and get started. It's about 11 a.m. now. So our agenda for today, just a brief couple things in Canvas regarding the USM laptop loan program announcement. I'll show that again. Some web links that I've put in an announcement, and then the Wiley Plus reminders for your homework 14, Orion 14, homework 15, and Orion 15. In preparation for your exam this Friday. So the exam 2, again, it's open for a 24-hour window, and you'll have 60 minutes to complete it once you start. Then today we'll do a putting it all together problem, as I call it, on structure elucidation. And then if there's time, we'll switch over these second semester topics from the workbook. So in the Canvas module or Canvas shell here, go to announcements. So let's go down to the first one, laptop loan program. So I know there were some people that
I can't believe she got that.
Who gave that to?
Hannah.
Oh.
So Anne, maybe if you could mute your mic, please. Thank you. So some students had some issues. Maybe they had Chromebooks or laptops that would not allow them to install the lockdown browser. Please take advantage of this laptop loan program available to you. That's the USM has purchased laptops through funds available from the USM Foundation and the federal government CARES funding. So please make sure you have a functioning laptop so you can take the exam on Friday without any issues. The next announcement was the organic chemistry web links. So again, these are alternative resources for you to use to supplement your education in this course. I'm a pretty firm believer that even though you have a course textbook, you know, that's one viewpoint. These other virtual textbooks are other viewpoints that may explain things in a way that you can more relate to. And the spectroscopy resources are really great as well for doing extra problems. So for example, let me just click on one here. So this is the web spectra at the University of California, Los Angeles. So if you look, there's beginning problems, intermediate 2, and advanced. So if you click on one of them, basically it's pretty succinct. There's a molecular formula. Then you can click on, you see NMR spectra. You can zoom in various regions. You could actually do that here. So if I put 5, 0, and then zoom. So this, I look at that and I say, bada bing, bada boom, that looks like ethyl acetate to me. You can look at the C13. So there's 1, 2, 3, 4. So you basically just do the sort of thought processes we've been approaching these. And what's nice about these is it's another resource. You can hone your skills on doing these sort of problems. Again, so if you need to zoom in, which I think everyone will probably need to, you can just type these numbers in here and you actually zoom in. You see the format of the spectra, you know, so we have doublet, triplet, quartet. So again, it's just more problems you can do, and the more problems you do, the more you'll understand the material. So the last thing I want to show you again is your module 2. Again, please, when you're doing your homeworks in Orions, access them directly through Canvas through these links. If you're already in Wiley Plus and you try to access them, your grades will not transfer over to Canvas properly. That's not a huge issue, but I've been getting a lot of emails about why that happens, and so that's the reason. So any questions on these announcements before we move on? So yeah, maybe let me go back to this real quick. And if you haven't already done so, in the announcements last week, I put this chat announcement to download the handout that we're gonna go over initially. So it's basically a spec problem we'll study. So that's where you can download it from and use the PDF or print it off and do your own markings. So I just wanted to start with just a review of a very practical review of NMR spectra and what it's used for. Again, there are 2 types that we're considering now for NMR. Proton NMR, which is shown at the top here, and then carbon NMR, which is shown at the bottom. So the proton scale is typically from 0 on the right to about 10 on the left. It extends to about 12 for carboxylic acid protons. But what this slide is showing you is where the different types of hydrogens occur. So we have saturated, again, that's sp3 hybridized carbon bearing H. And again, we're detecting the hydrogens on this top spectrum. So allylic hydrogens, hydrogens that are bonded to carbons bearing an X heteroatom, such as oxygen, nitrogen, whatever, halogen. Vinylic, so vinylic means the hydrogen is bonded directly to an sp2 hybridized carbon. Those are typically your alkane functional groups. And notice that's separated from aromatics, which are bonded to the benzene ring. Aldehydes typically occur at about 9, and then your acids, like I said, around 12. On the carbon scale, notice it's much larger. It's from 0 to about 220. It sort of follows the same trend. Now we're looking at the carbon itself. So saturated sp3 hybridized carbon, carbon bonded to a heteroatom, carbon bonded to alcohols, sp hybridized alkyne carbon, vinylic sp2 hybridized carbon in alkene, sp2 hybridized carbon in aromatic, and sp2 hybridized carbonyl carbons. So what is the big picture of this? You know, as we look at molecules and we drill down and start defining different functional groups, different types of C's and H's, you see they're spread out along these spectra. So what that means is there's resolution amongst them, and we can figure out what is the exact nature of a compound. So we can refer back to that as needed. Maybe let me look at the chat here real quick. So Elijah is asking, is the second exam going to have stuff from the first exam on it? It will, in the sense of the concepts are cumulative throughout this course. So you have to know the concepts from the first module to understand concepts from the second. But the specific exam 2 is only on chapters 14 and 15. So Carly had asked about chemical shift. So let me explain that again. So for both of these spectra on the x-axis, the chemical shift is defined as the Greek letter delta in parts per million. And we're looking at the right side, which is 0. And so when you see a chemical shift, it's always moving from 0 on the right to the left. So if you see a signal at 1.5, that's the chemical shift in parts per million. So 0 is defined as a specific region, and then you're moving to the left.
Kind of like the placement of the I don't know how to just like chemical shift placement on that chart.
So can you repeat that again?
Is chemical shift like the placement on that chart, pretty much, is what you're saying?
Yeah, so if I said there is a singlet at a chemical shift of 2.5, you'd basically, your eyeball would read from left, or excuse me, from right to left. You'd hit 2.5, and at that region of the spectrum, you would see a singlet.
Okay,
So,
thank you.
we'll see it in. Let me just give you a preview of some of the problems we'll do. So this is a problem we'll go over in a little bit. So see the chemical shift. It says a chemical shift of 1.28 parts per million. There's a singlet that integrates to 9. So notice in the way this data is presented, you're not actually seeing the spectrum. So what you infer is by this chemical shift, what type of hydrogens those belong to based on the region it lies in. So let's go through this problem, which I've mentioned. The PDF is uploaded. I'm going to switch over to the doc cam. I'm going to do the writing on the document camera, but this slide will be up for you to see. Just let me know how the focus level is. I think Jordan, maybe if you want to, oh, thank you. So basically, if I can't fit this all in doc cam, but we're going to put all of this data together. And if you notice on the slide, there's a Post-it note covering up a piece of data. And that piece of data actually gives you the molecular formula. I'm not showing it to you because I want to look at all this data and then propose a molecular formula. And then from all of that, we'll figure out what the structure actually is. So let's go ahead and get started. I'll ask you some questions. So let's start with the IR. When you look at the IR spectrum, is there a functional group that you recognize? So we have a couple of early responses here that say carboxylic acid. And I guess you can't see what I'm writing, so I'll move the page up. So this is what was in the chat. So again, part of really understanding this class is we want to convert these words into like a fragment of the functional group. So I'm going to convert that into this. So that's what we recognize in terms of the structure of a carboxylic acid, right? So if I look at that and then I say, well, this, and I can condense that to CO2H. So why is this useful? So we're already starting to build up the molecular formula, right? We have a fragment. We see that, okay, there's 1 degree of unsaturation, and here's some elements. So what is, from 35 to 2500, what does this belong to? This part of the spectrum. What is that? How can we assign that peak? So yeah, we'll call that the OH. So that belongs to the OH stretch of the acid. And then what does this belong to? This peak at 1715, this sharp, intense peak here, what does that belong to? So presumably when you looked at the spectrum, you saw those 2 elements, and in your mind, you immediately thought carboxylic acid. This is the connectivity of the elements in that carboxylic acid. There's 1 degree of unsaturation. And then we're already on our way to building up the molecular formula. So at this point, we've pulled out basically all the information we can from an IR. And again, anything sort of to the right of 1500 we ignore. just because it gets too complicated. So let's look now to the mass spec. And again, I'm not giving you the molecular formula, which is written there. So it's written right there. I'm not giving it to you because I want you to figure it out. So what is the parent ion in the mass spec? So we have the parent is shown as 74. So in a prior email, Mac had asked, how do you know when other elements are present? And so you have to make some assumptions. But we already know from the IR data that we have 2 oxygens, right? So we know there's 2 oxygens present. So we're going to run with that. And what we're going to do now is figure out what are the contributions of carbon and hydrogen to the remainder of the molecular formula. So we can take 74, that's the parent, and again, the parent contains all the elements in the ratios in the molecular formula. The parent 74, we know there's 2 oxygens. So we're going to subtract 2 times 16. That should get us what? So that gets us 42. So now we're operating under the assumption that what's remaining in this 42 is only carbon and hydrogen. So the max number of carbon is what? What should we do to figure out the maximum number of carbons? So Hannah's quick on the draw. So that the number seems appropriate, but how do we get to that? So 42 divided by 12. Again, 12 is the atomic mass of carbon. Again, you're going to get some decimal, but you should always round down. That's the best practice. So that gets 3. So then we go back and we say 42 minus 3 times 12 is equal to what? So that gets 6, and that's the max number of hydrogens. So what have we done? We have 2 oxygens, 3 carbons, 6 hydrogens. So now what we want to do is we want to verify our observation here that there's 1 degree of unsaturation in this molecule. So again, we pointed that out with the carbonyl group of the acid. Why can't we do 74 minus 12? So Hannah is asking about minus 12, minus 1, presumably from this fragment here. The reason I sort of don't want to go that way is because you're still going to have to go through this logic anyway. I mean, you can certainly do that, which is fine. You'll end up with the same molecular formula no matter what. I just went through this way because it's a little bit more straightforward because you're getting all of the carbons in one calculation, basically. So we're verifying the degrees of unsaturation, CnH2n plus 2. So n equals 3. So for a fully saturated carbon chain with 3 carbons, that should be 8. We came up with C3H6O2. The oxygens don't do anything to the hydrogen count. So we get H2. A degree of unsaturation is defined as a molecule of H2, so that gets us our 1 degree of unsaturation. So that matches this. So now let me show you in another way of sort of, now that we have the molecular formula, we've proven there's 1 degree of unsaturation. We're still going to look at the NMR data, but what I want to go through now is another way of thinking about how we're going to convert the molecular formula into a structure. So maybe I'll get out the green pen here. So molecular formula, sorry, C3H6O2 with 1 degree of unsaturation. So the logic that we're going through now is really meant to help guide you so you're not proposing like something that will violate the existing data. This is our molecular formula, C3H6O2. We already found from the IR CHO2, which was 1 degree of unsaturation belonging to this fragment, correct? I'm going to write this fragment of the acid with a squiggly line. That means something has to be bonded to that carbon. That's all that means. I'm just accounting for CHO2. CHO2. I'm going to subtract that out now. C2H5. This is what remains, and that has 1 minus 1. That has no degrees of unsaturation. So what does that tell you? There's no rings, there's no double bonds, as Tenley points out in the chat. So these carbons must all be sp3 hybridized. So before I write what that means, does anyone want to, in the chat, spend a minute or so and see if you can figure out what the structure is? And then write the name of that structure in the chat before I go through this logic. See if you can take that information, see how these are bonded to that, and then I'll write it down. So based on the earlier responses here, Hannah and Aiden basically are saying the same thing, that the C2H5 group has to be an ethyl, and Mac, Garima, and Ian all point out it's propanoic acid. So yeah, this has to be the following. You have two carbons, and again, this is Lewis structure building here. Two carbons, they have to be bonded to each other. They're sp3 hybridized. We have 5 hydrogens. We plug them in. This still needs a remaining bond. So this fragment is the ethyl group. So what we're doing now is we're taking this existing fragment we know, we're bonding it to that fragment. And so what we're ending up with in the bond line formula is this structure here, propanoic acid. So I don't know how many of you have sort of thought this way, but maybe this is a good class to introduce you to thinking this way. Propanoic acid is our claim. So this is sort of how lawyers talk. If you have ever read a patent, in a patent, you're claiming something. So we are claiming that this is the structure given that data. So now let's go back and look at the NMR data to see if our claim is verified. Or is the structure really propanoic acid? So I'm gonna show the NMR data now, and we'll walk through that to verify our claim. And again, I think as you become adults, you really want to have evidence and back up your claims. You just don't want to be spouting things off. So that's sort of the logic of what we're doing here now. First, let's look at the carbon 13. And again, this may be a little light on the doc cam. So what I'm going to do here real quick, I'll sort of darken these peaks. So let's initially look at, so again, this is carbon. Again, we're at 0 to the right, 220 parts per million to the left. We're only looking now at this bottom one here called the proton decoupled. That's the one we're looking at initially. This is our claim. So in our claim, how many unique carbons are in propanoic acid? So we see some responses of 3. Now, when you look at this proton decoupled spectrum, and we ignore this peak here, solvent, we're ignoring that because that is the liquid that the sample is run in, so we ignore that. How many peaks do you see in the carbon NMR, the proton decoupled spectrum on the bottom? How many do you see? So that is the connection of when you look at the molecule and I'm asking you the unique type of carbon, this is what you're really thinking about is the carbon NMR. So you see 1, 2, 3. Now when you look at those, see the resolution of those peaks? See how they're separated? You have a peak pretty close to 0. You have one, say, about 30, and then you have one at about 180. See that these two are sort of clustered, right? And then this one's really far away. When you look at these, another way you can sort of narrow them down of the 3 carbons in this molecule, how many are sp3 hybridized? So we have some 2 responses. How many are sp2 hybridized? And so we've accounted for 3, so this has to be 0. So now, when you consider these numbers here, can you see a correlation between where they lie on this spectrum? So in my red marker, the numbers I'm putting in now are the numbers for how the compound would be named. So this has to be carbon 1, 2, and 3. So maybe what we can do is I can write 1, 2, and 3. And then in this column, I'm going to write the chemical shift in parts per million. I'm trying to keep all this sort of visible at once. It's going to be kind of difficult, so you might have to refer back to the screen. Carbon 1 has what chemical shift? Taka is saying carbon 1 is 180. So yeah, hopefully that's clear, because see how this had a different hybridization? So it's from our determination over here, there's only one of them. That one is separate, so I think that's a good assumption. Then now maybe 2 and 3 are both sp3 hybridized, but they're different in the following sense. We can say that 2 is allylic and 3 is not. So allylic is directly bonded to a carbon in a double bond functional group. So maybe what I can point out to you now is what this means right here. See this DEPT? So that stands for distortionless enhancement by polarization transfer. You don't really need to know or understand the phenomenon of that. What you're looking at right here is the key. This is another type of carbon spectrum. And what this is indicating to you is that CH2 groups appear down or negatively phased. CH3 groups are positively phased, so they're on top. And CH groups are also on top. So now in these last 2 assignments, what would you say carbon 2 is of the last 2 assignments here? Carbon 2 is at what chemical shift? Keeping in mind that CH2 groups are negatively phased. So some early responses about 29, 30. Yeah, we'll just go ahead and put 29. So what I mean by that is, see how this peak is down? This is a separate experiment in the NMR that is stacked with the original carbon. So we have an sp3 hybridized carbon. This group is negatively phased, so that means it's a CH2 group. So there's only one of them that's carbon 2. So we have one left, that's CH3. So that has to be our third carbon, which is a CH3 group. About what, say 10? So we've done the actual assignments based on the given data. Let's see if I can get more of this on the screen at once. So again, the red numbers are how the compound is named. The green numbers are the associated assignments in the carbon NMR data. So is the concept of carbon and then this depth clear to everyone? So I'm getting some positive responses. Again, if it's not clear, send me an email and we'll set up a Teams invite to meet for 30 minutes and go over this. So what we're going to do in this last part, we're going to look at the proton NMR. So proton NMR spectrum. But before we do that, let's just think about the molecule first. Let's conceptually do a thought experiment, and then we'll look at the data and see if it matches our claim. So I'm going to put the numbers in for the nomenclature again. So how many unique type of hydrogen are in this molecule? Unique type of hydrogen. So we're getting some 3s. And then what is the ratio of those 3? So 1 to 2 to 3. So we can see that, right? So here's 1, there's 2, and then there's 3. So now let's look at the actual proton NMR data and see if that's confirmed. So again, here's 0 at the right, and we're reading to the left. There's 10. But it's showing you in here there's an expansion where there's a peak at, say, 11. So even though I didn't I didn't write a number there, I'm going to just write 4. And so what these numbers mean, you can think of them as like area under the curve. So what I'll do is I'll just write those numbers: 4, 8, 12. And so if we wanted to find the ratio of those areas to one another, we would divide by the smallest number, and that's 4. So here are those, I'm going to just call them areas. Then in column 2, I'm dividing all of them by 4. So 4 divided by 4 is 1. 8 divided by 4 is 2. 12 divided by 4 is 3. So now look at how that matches with what you just thought about. So actually, okay, yeah, what we can do, again, let's start at the right-hand side of the spectrum here and read left. So we're running into this peak here that had an area of 12, and we just determined that that has 3 hydrogens bonded to it. So that's a CH3 group. The chemical shift of this, I'm going to say, is like maybe 1.1. So I'm just going to erase sort of that and say at a chemical shift of 1.1, we have an integration of 3. That's an assignment of a CH3 group. And so the only CH3 group on the molecule is at carbon 3. So I'm just writing, that's the assignment. That CH3 group belongs to that group there. And then it might be hard to read, but what sort of peak shape is that? And again, the question I'm sort of asking you is, how would you describe that peak? So the peak at 1.1 has what look or shape to it? So singlet, doublet, triplet, quartet, tall. Yeah, it's Carly says quartet. She can't really see. So the logic you can use is that even if you can't see it visually, when you're looking at this CH3 group, how many neighbors does it have? Again, we're considering this peak here has how many neighbors? It has 2, so we use the n+1 rule. 2 plus 1 is 3. So this peak becomes a triplet. So that's what it looks like if you zoomed in on it. So now we said this second peak here, it had 8, and it came out to 2, so that's a CH2 group. So that has to be, we're at a chemical shift of about 2.4, integrated to 2. So it's a CH2 group. So we're going to do the assignment to position 2 there. So using that same logic, how would you describe this peak? Again, it's this assignment. How many neighbors does that, how many hydrogen neighbors does that group have? So yeah, this would be a quartet. So we've done the assignments of the CH groups. The last remaining one, again, at about 11.1 or something, that integrated to 1, so that has to be our OH group. So Hannah is asking, how can you tell quartet versus triplet? So let me get to some clean paper here. So again, when you're determining this term called multiplicity, So the difference is when you're looking at carbon versus hydrogen spectra, why do hydrogen look different? Why do they have this multiplicity? So when we're considering this peak right here, what do these hydrogens look like? Even though these are all the same, these hydrogens are split by the neighboring hydrogens on this carbon here. So we see there's two neighbors. We use the n+1 rule, that gets us 3. And the term for the n+1 is triplet. So that's what those peaks look like, is a triplet. The multiplicity is determined by the neighbor. So when we consider these two hydrogens, now there's no neighbors here, 0. There's 3 there. n+1, that gets us 4. So these 3 neighbors plus 1, that splits this into a quartet. So maybe what I can do now is just take a couple minutes to maybe explain a little bit about why that is. So it's always important to get sort of a deeper understanding. Go over to this slide now. We're back in the slide deck. And so this slide is called NMR Basics Splitting and Multiplicity. So if you've watched Wedding Singer, you know this song. So this describes the n+1 rule. And again, the splitting is always determined by the number of hydrogen neighbors. And what I've written here, to a first approximation, all the unique types of hydrogens you can think of as just a singlet. But in reality, that's not true because of spin-spin coupling. The coupling leads to splitting, and the splitting leads to the multiplicity. So if there are no neighbors, your peak will always look like a singlet. If you have one neighbor, the n+1 rule says the peak will then split into a doublet. 2 neighbors is a triplet, 3 is a quartet, 4 is a quintet, 5 is a sextet. So the location of the signal is dependent upon the functional group. The presence of neighboring hydrogens and their count influences splitting of the original signal. So one thing we talked about last chat session was look at this, look at the height. For a singlet, the height is the height. For a doublet, the two sort of signals or peaks match each other in height, right? They're equal ratio. But now for a triplet, you can ask, why does this height, why isn't it the same as that height? So remember, this was 1 to 2 to 1. Now for 3 neighbors, a quartet, it's 1 to 3 to 3 to 1. For the quintet in sextet, you see that the outer peaks progressively get smaller, but they all sort of culminate where the middle peak is the tallest. So where does that come from? That comes from the Pascal's triangle. So in our 0th row, I'm calling it 0th row, but you can think of it as number of neighbors. With no neighbors, you have a single peak, that's a singlet. With one neighbor, you're now split into a doublet, and the ratio is 1 to 1. So that's where that 1 to 1 equal intensity comes from. So Hannah basically, instead of using the word tall, we can use Pascal's triangle to describe the intensity. So now if you have two neighbors, you're split into a triplet, and the ratio of peak heights is 1 to 2 to 1. So see what we see, 1 to 2 to 1. Three neighbors as a quartet with intensities 1 to 3 to 3 to 1. So you can see for 4 and 5 how these intensities basically change. And again, there's 1 along the outer edge. Then these inner ones are basically the sum of the two numbers above them. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then 1. Any questions on that before I go through 3 more slides to maybe show you how this phenomenon arises? So Carly asks for the quartet. So again, these two hydrogens appear as a quartet. So those two appear as a quartet. And the reason that is because of these neighbors here, 1, 2, 3. So 3 plus 1 is 4. They split this signal into a quartet so that the counting of 3 is there for that peak. So again, I take a very practical approach to teaching this. I don't really like teaching the theory of it because what will make most sense to you is the practical interpretation of the data. And so the theory, it's pretty easy to just get lost in it. But I'm going to give you a very simple explanation of why these things split to begin with. So to a first approximation, if we go back to the document camera, all of these hydrogens on this methyl group are equivalent. So when we're thinking about a unique set, they should be one set, one peak. So that would be a first approximation, a singlet that integrates to 1, or excuse me, that integrates to 3. So for this specific one that's shown, we're just considering one neighbor. So a singlet that would integrate to 1, that hydrogen has one neighbor, so a second approximation, we get 1 plus 1 is 2, so it's a doublet. But what is the origin of this peak shape? So the actual phenomenon, and again, remember when we talked about IR, why does the signal even arise? Because the IR light is hitting the bond dipole moment. Why do you even see a signal in NMR? You see a signal because of the spin state of the proton. So the hydrogen nucleus spins. You can think of it as like a top. If you remember as a kid, a top is like a toy that you spin and it spins. And eventually, at some point, it'll start to wobble. So that's the phenomenon that you're seeing when you see this signal. The spin can be either spin up or spin down. So the signal that you're looking at is affected by the spin of the neighbor. So if your first approximation, the unique set is a singlet, but you have one neighbor, and that one neighbor can be spin up or spin down, and that's what we see why it splits into a doublet. These terms here, upfield, shielded, low frequency, that's towards the right or 0 of the spectrum. Downfield, deshielded, high frequency, that's towards 10 or the left of the spectrum. So I know that's a lot to take in. Let me just show you the other two examples I have slides for, and then we'll finish with some problems that are more practical in nature. The signal you're interested in to a first approximation looks like a singlet, but now it has two neighbors. So the hydrogen has two neighbors. Our second approximation is now a triplet. The reason it becomes a triplet is because of the spin states of those neighbors, which are following. Both spins can be up. You can have one down, one up, one down, so those match, or they can be both down. This sort of resembles that logic that we used in mass spec when there were like two bromines, in a sense. So this we have 1, 2 to 1. It's telling you the spin state of the neighbors. And again, this may not be terribly clear, and it's probably more of a theoretical explanation. But the important thing for you to do, the skill, is to be able to interpret NMR data. And I think the sort of practice problems we've done so far has given you the skills to do that. This is just more of a theoretical explanation. So what about for three neighbors? Again, the signal initially might look like that. Three neighbors would look like a second approximation being a quartet where you have n+1, and then you would draw out the spin states. So if you were to do that on this end here, you would have, say, three up. Over here, there would be three down, and then these two would be a mixture of those different spin states. And I'll create a screencast that explains that in a little bit more depth, but that's more of a theoretical explanation for understanding why you get these different splittings. Let's just close on three problems here that you can answer in the chat. So consider the question, what is the splitting of the indicated hydrogen? So again, we're trying to determine what these two hydrogens would look like based on the number of neighbors. So count the number of neighbors, do n+1, and then write a letter in the chat box. So the primary responses are D as in dog. And again, it's important for you, just like you're crossing the road, as we learned in grade school, to look both left and right. So there's no neighbors here, right? Remember, you always got to look both ways, left and right. There's none there. There's 1, 2, 3 there. 3 + 1 is 4. We count 1, 2, 3, 4 lines. Quartet, D is the correct answer. Here's the same molecule, but a different position. This CH2 group should now look like what? How many neighbors? Do n+1, and then what should the peak look like? So I'm seeing C as the response, so no neighbors. 2 + 1 is 3. That's a triplet. 1, 2, 3. C is the correct answer. Then we'll finish off with one more. What about this CH2 group? Now you have to look both left and right. So we count. We have 3 neighbors here, 2 neighbors there. That's 5. 5 + 1 is 6. We count 1, 2, 3, 4, 5, 6. So A is the correct answer. So we're about out of time, but that's been sort of a really practical explanation of how you interpret NMR and you do structural elucidation by putting all the data together using IR, mass spec, and NMR. So on Wednesday, I'm pretty excited about Wednesday's lecture. We're going to dig a little bit deeper into this compound, which we've saw already, 2-butanone. And what we're going to do is we're going to look at this. This is actually called 2-dimensional NMR. And this is what one of them looks like. So this is like a contour plot. And we're going to look at sort of our eyeball looking down, what these contours mean, and how we can use more advanced experiments to help us do structural elucidation. So again, that's more problem solving and logic. So hopefully we'll see you Wednesday for that. Again, get to work on your assignments that are due Friday. If you need help, shoot me an email and we'll set up a Teams invite. But other than that, we'll see you then. Take care.